Everyone had a chance to come in. Right. So today's talk's what's new in QEMU. The first half of this presentation is going to deal with what's come up in the QEMU releases so far and the new features that have been added. Once I get to talking about the M profile, I'm going to segue into having a bit of a wider discussion about QEMU's microcontroller support and how that relates to the Internet of Things. And that's mainly looking for feedback from you guys of what sort of things you'd like to see. So since the last Connect, there's been one major release, 2.8, and the 2.9 release is currently ongoing. So we're approaching hard freeze, and the first release candidate is going to be tagged fairly soon. We're seeing releases at about a 3 to 4 month cadence. So typically, you'll see a release in April, August, and December. So let's talk about 2.8. So as ever, if you want to see the full list of everything that's been changed, the changelog is kept on the QEMU wiki. I'm just going to really talk about the big changes that are specific to ARM here. So for KVM, one of the biggest changes is the interrupt translation service support. So this is something that allows for message signaled interrupts that can be sent to GIC-v3 enabled VMs. This is important for a number of applications. For one thing, vhost requires it, but it's also useful for device pass-through, especially if you have hardware that supports virtualized functions. So things like SRIOV enabled network cards that present virtual network cards to your guests. There have also been a number of updates to the tiny code generator. So this is often referred to as TCG mode. The TCG is responsible for QEMU's cross-architecture emulation abilities. So the TCG ops an intermediate representation which is used by the JIT engine when you translate guest code into host code. Previously, atomic operations in QEMU tended to be dealt with hand-coded helpers for the various architectures that needed them, and generally only for Linux user mode. We've now got a architecture-agnostic set of TCG operations, so you can model atomics for all architectures using a common baseline. At the same time, there was also support added for barrier and fence instructions. So we generally tended to skip the implementation of this on system emulation because it didn't matter when you were running everything single-threaded. And you also tend not to see the effects of it in the normal use case when you're emulating a weak memory order system on a strong memory order system like x86. But it was incorrect. So now it's properly modeled. So when a guest issues a barrier instruction, you can see things behave as you would expect. This doesn't solve the reverse problem if you want to run strongly ordered guests on a weakly ordered system. So if you're trying to emulate x86 on an ARM system, for example, you will still see some problems due to the differences in memory orders. Finally, in 2.8, there was a complete re-engineering of the exclusive mechanism. So this is an internal system for QEMU which allows it to suspend all of the emulation threads when it wants to do something system-wide at an atomic level. It's used in two places in 2.8. The first is supporting oversized atomics. So not all architectures, generally architectures will support atomic operations up to the bus width, except some of them like x86 allow you to do 16-byte atomics. And the way that we do that, if you're running on a system that only supports 64-bit atomics, is to freeze the whole system, do the atomic operation, and then start again. It's slow, but it works. The second is it was used to make the TB flush operation, which has long been marked in the QEMU code as this is not thread safe, to make it finally thread safe. So this is when QEMU is doing its translation, eventually the translation buffer gets full up with code, and at that point it needs to throw all those translations away and start again. And now it does it safely, and it doesn't crash. So with these updates and Peter's syscall work in 2.7, Linux user emulation is now much more stable for multi-threaded programs. It used to be when someone said, I've got a problem with Linux user, we said, is it multi-threaded? And they said, yes. We went, tough. Now you stand a much better chance if your multi-threaded program's working.
Question. These days we say please file buggable.
Well, yeah.
When you said there are still issues with emulating strongly ordered on weakly ordered, do you mean there are issues with emulating strongly ordered on weakly ordered, or do you mean that programs that weren't doing any sort of portable synchronization type stuff will fail because they would have done anyway if you compile them to the other architecture?
Yes. So yeah. So if you compile something for a strong architecture, typically the compiler will not bother to put barriers in where it knows it doesn't need to, because the load stores have an implicit memory ordering. And yeah, and if you run those on a weak system, those ordering constraints go out the window and things will fail. So yeah. So for QEMU 2.9, this is currently rolling, so I don't know when the release candidate will be out, but it'll be soon. And the speed of the release will be dependent on how many bugs I've introduced in the last patch that I sent. However, all the features I'm going to talk about have already been merged into mainline, so if you build from master, you'll see them. So the first thing, TCG has finally gained EL2 support. So this built on previous work when we added EL3, which is otherwise known as Trust Zone. So now we fully support the hypervisor exception level, which, as you can tell, makes the KVM developers very happy. So you can now boot up a KVM machine, and then in your emulated KVM machine, boot up a guest. And it all works. This is still slow compared to using real KVM, but it's faster than having nested TCG. It also means you can use QEMU instead of the fast model when you're testing hypervisors, unless you need some of the specific features that only the fast model supports. Now, this is also useful given the next feature. This is the Multi-Threaded TCG project, so known by the catchy acronym as MTTCG. Now, some people will know this is a project close to my heart because I've been involved with this for about the last year. It finally removes the single-threaded bottleneck from system emulation. So this isn't a performance panacea, but it does mean you'll see a performance improvement for SMP guests in system emulation, as long as you have at least that many cores on your host system. It tails off at about 8 CPUs, but it's definitely a lot better than it used to be when everything was pegged to one CPU. Hmm? Yeah, I mean, you could boot with SMP4 on TCG. It just wouldn't take 4 times less. Yeah. So, I mean, this project has been a long one. It's involved work from quite a large number of companies, community contributions, and also the academic community has been involved. So it's taken several years to get to this point. And I think when I first suggested that this might be something we do in QEMU, Peter went, QEMU's never been designed for that, that'll never work. So it has involved quite a lot of re-engineering of core bits of QEMU. We committed a lot of work. And you were right, it was a lot of work. So there's, apart from all the stuff that's come from upstream, we spent quite a lot of time reviewing other people's code to help it in its journey upstream, and we've also written quite a lot of code ourselves for supporting the ARM enablement. And the final patch that we were also responsible for maintaining on its way to the upstream merge. So the core technology that MTTCG relies on is target agnostic. It was very important when we started that this wasn't going to be a ARM-only solution. We wanted something that could be used for all the guests. Having said that, at the moment, ARM and AART64 are the only 2 guests that you can that it's enabled for by default. x86 on x86 running in TCG mode, has been tested. There are patches ongoing to do it. And some enterprising student has even run x86 on AArch64, so they have added additional patches to get around this mismatch in memory models, and they've actually booted an SMP Windows on an AArch64 host. Very slowly, but there might be tricks we can do to make it a bit faster.
Is there by any chance put a memory barrier in between every single memory access?
Yeah, so that's basically what you have to do. So at the moment they're using the existing memory barrier support and adding explicit memory barriers for all loads and stores. He's currently looking at optimizing it. We might do better if we start generating load acquire store releases instead of normal load stores, but that's an ongoing experiment. It's an interesting academic exercise. Whether it will be useful to people in the real world.
For world domination.
We are expecting the other architectures to submit updates to enable MTTCG by default, probably in the next release phase. So I'm aware that the MIPS maintainer has been maintaining a series. I think the PowerPC guys have done stuff on this. So once this release is out, there'll be more architectures enabled. So finally, there have been a number of fixes to the Cortex-M series emulation. And there's been an effort by Linaro to ramp up QEMU's microcontroller support. So far, the fixes have been aimed at architectural aspects, which we knew were broken, but this seems like a good time to segue into talking about the QEMU and the Internet of Things. So M-profile CPUs are different in a number of ways. The main difference is they're microcontrollers, so they're not application processors. So they're usually aimed at smaller, low-power solutions. Being microcontrollers, they're not really designed to run a full-stack OS like Linux. So they have a much simpler memory subsystem. They have a memory protection unit instead of a full MMU. They also have a different exception model with a different interrupt controller. So there is a NVIC instead of a GIC. And usually they're running some sort of custom run loop or a very small RTOS that gives real-time guarantees for whatever application they happen to be running. So QEMU already models quite a number of microcontroller class ARM boards. The two main ones are the TI Stellaris one and the NetDuino 2, which is actually a development board that targets Microsoft's .NET. But they're all based on Cortex M3s. However, there are a number of issues. So Linaro, as I said, has been very focused on the A-profile processors so far, and there's not been much community activity in supporting the M-profile stuff beyond fixing the odd compilation program if you break a compile when adding another feature. So this has led to a situation where we've had some long-standing unfixed bugs and some important features missing. So, and also, as the architecture has progressed, the support for the M-profile class CPUs has also lagged. So things like FPU support and the V6M profile currently need some love. There's also a V6M.
V6M is the really cut down version of V7.
So that's the Cortex M0 and Cortex M0 Plus. Another problem you come across with the M-profile boards is they tend to be very minimal hardware-wise. Because usually most of them are prototype boards, so they basically give you a CPU with a bunch of GPIO pins, which you then connect up to your project. So it's kind of unrealistic for QEMU to model every homebrew project that someone can build up with one of these IoT boards. But at the same time, there isn't really any way QEMU can connect to any external simulation if you want to sort of like simulate a project that you've put together that puts one of these boards together with some other devices. I will note there are some third-party forks. So some of the chip vendors have got forks of QEMU that do this sort of thing. So they'll use QEMU to simulate an ARM core, and then whenever the ARM core writes to a device, they'll connect it in using some IPC to something that models an FPGA, so they can run their FPGA simulations together with ARM. But none of this has ever come upstream. So one thing I'll be interested in hearing feedback on is whether we need to have this sort of ability to connect QEMU to external simulation to make the M profiles useful.
Well, Android emulator has buttons and
Yeah.
LEDs, I think.
Yeah, and when we did, so we previously did some work on the Android emulator, and again, that was just a bunch of special devices that could be poked at, but I think it was with ADB and their own setup. So the work so far, in the last cycle, there was a bunch of work to clean up the MVIC emulation, so that's all fixed in 2.9. There's even a nice set of bare metal tests that actually exercise this code, so we're fairly sure it's good. But other tasks on the list, and this is where getting some sort of sense of what people want in priority would be useful. The MPU needs fixing. Now, this is a simplified memory controller, so it doesn't give you all the full features of an MMU, but it does allow you to protect bits of memory and do stuff like that. FPU support, so you can get microcontrollers with the FPU. QEMU already supports pretty much all of the FPU instructions for ARM, so that bit can be reused, but all the exception model is completely different from the application profile. Finally, there's support for supporting the newer chips, so the V6M, the Cortex-M0, and the V8M, which is a 64-bit microcontroller, which I find slightly stunning, but there you go. So to help Linaro with setting its priorities with respect to this ongoing work, I'd like to open up for questions. So specifically, are there use cases you're looking to use QEMU to help solve? Should we be looking at modeling any other complete hardware? And are there any other requirements people would like us to take into account? Now, I will stress now, we have limited resources, so this is about priority setting. This is not about promising what will be provided. There are two options for M-profile boards that we've been thinking about. The first one is the BBC microbit. So I don't know, is anyone familiar with the BBC microbit here? So this is a project that the BBC in the UK led to get hardware into the hands of children. The reason it's interesting is because unlike a lot of these other boards, it's actually got a number of devices on it. So because the whole point of the microbit was you could give it to a kid, they could write some code and immediately get things to happen. So it's got a LED array and some direction and movement sensors, so you can actually do useful things with it. The other potential board is the 96 board's Carbon. It's got quite a bit of a beefier processor. It's a Cortex-M4, and it's got more memory. But really, other than the USB and the Bluetooth on it, it hasn't got anything built in because you expect to connect it to external devices. So with that, I think I should open up to any questions, thoughts, queries about our M-profile support.
How do you emulate Bluetooth in QEMU? Just curious.
Yeah, there's quite a full stack that's involved in Bluetooth, so I don't know if you can plug it into Linux's own system or not. But to model a chipset with Bluetooth and how you would integrate doing Bluetooth in. So what is that emulation? So is that for where do the Bluetooth packets go basically on your emulation?
One of ways for using the in-computer dongle as a kind of pass-through to QEMU, and there was some other modes for it, but I didn't use that much.
So you fed the Bluetooth data to a real Bluetooth on the host.
Assign your Bluetooth dongle not as USB device, but as Bluetooth host dongle
Right, yeah. Yeah. So I assume you have something externally to then talk Bluetooth to your model. Any more questions?
Yeah, so when it comes to microcontrollers, MCUs is usually gives impressions that it's very fragmented and fork support. For example, are you aware of the GNU ARM Eclipse QEMU fork, which kind of it's support for dozens of Cortex-M boards?
So I am aware Eclipse have something. I've never actually looked at it in detail.
Yeah, it's unclear how much of GNU, of ARM, of Eclipse in this particular project. So I wondered if you're aware of it at all, and do you know people? It's hosted on GitHub and all that stuff.
Yeah, so this is so that's a fork of QEMU, and it's kind of the guy who's very focused on M-profile support, and he's got some support for using CMSIS board definitions to kind of automatically generate models, and so it's all kind of interesting, but it's the usual kind of thing. It's like there's a lot of code there. It's not clear how upstreamable some of it is.
Yeah, but do you cooperate with them? Are you like, do you have contacts or?
Mostly for us in upstream QEMU, it's kind of the other way around. It's do other people cooperate with us?
Yeah. So
it's like if
do they?
So in this case, he participates a bit on the upstream mailing list. He doesn't really submit code.
Okay, so maybe they need some prod, and maybe they don't know that like it's common in open source project upstream. Maybe they don't know it.
Yeah. So I mean, in this case, a lot of what he's doing is there's a lot of UI stuff. There's a lot of integration with Eclipse, which is kind of a bit adrift from upstream QEMU's focuses and biases. The CMSIS board definition stuff is also interesting because it's a sort of license-wise is if you generate a model from a CMSIS board definition, then what's the license on the resulting code? Maybe depends on what the license on the CMSIS file was.
Okay, and I have another question, if you allow.
Sure.
What about allowing to write plugins for QEMU for like specific device emulation in high-level language, in scripting language, not in C, because it's way too complicated or boring or effortful?
Maybe you'd be best to talk about plugins.
Well, so yeah, so I mean, this is one of the things you get with microcontroller stuff. So for A-profile boards, you can get away with saying, well, we model a couple of boards, and that's okay because people really just want to boot Linux, and then it's user space they're interested in. With M-profile, people care much more about the specific hardware, and they maybe want to be able to model the stuff that they have. For which, as you say, you don't really want people to have to write a bunch of files, programs in C to do this. But there is basically no support in QEMU for this, right? So all the APIs for devices, those are all internal APIs. They change a certain amount. It's all C, and there is no kind of idea of a sort of a higher level binding for that kind of thing. It would certainly be nice to do it, but that's a huge amount of work there, right? You've got to spec this stuff. You've got to get consensus with upstream for, is this something we want to do at all? What's the model for this? How do we do it? What's the licensing on the devices you provide? And we could do it, but it kind of feels like quite a large amount of work for Linaro to be doing. But yeah, this is one of the challenges with the whole IoT space is QEMU traditionally approach has basically been, we provide you a handful of models and they're probably good enough. And I don't think you can really treat the IoT space quite the same way because it's no longer sufficient to just say, well, we boot Linux, that's all you really wanted. But it's not clear strategically what does the IoT world want from a model in terms of what kind of a product are you trying to provide people. And there's quite a lot of work that moves away from QEMU's sort of core strengths. So yeah, it's interestingly difficult.
I see. Okay.
I'll just add to that. When you start embedding scripting languages into a core product, you'll also get people telling you you chose the wrong language. So there's a difference between embedding a scripting language into QEMU or coming up with a protocol that you could plug anything into. As you know, if you had an agreed protocol, and then they can implement their model in whatever language they like. But that's just another consideration.
How about systems that are mainly built around an A profile, but use an M profile as some, coprocessor, service processor, and do we have any plan to model something like that?
So there have been efforts in that sort of direction. So I know some of the third-party trees emulate systems where they have a variety of different cores, and they use IPC to talk between various instances of QEMU. There have also been attempts to break apart the code generation in QEMU a bit, so you could actually instantiate one processor of this type and one processor of this type in a shared emulation environment. But that effort has stalled as far as I'm aware, so no one's actively pushing for it. It would be nice to be able to do, though. So.
Yeah, thanks for the progress on the Cortex-M side. So if I was giving feedback, I'd like to see the MPU modeled. That would be good for us. And then on the V8M side, secure, non-secure mode. The major feature for V8M is secure, non-secure.
Is the existing trust zone stuff going to be?
Yeah, so just to kind of clarify for people who may be not quite so familiar what V8M is, it's I mean, as you say, the key feature is the secure, non-secure support, but it's not the same general architecture as trust zone is in A profile, so it's you get kind of the same high-level features, but the implementation is significantly different. So, yeah, you're right. That is basically that would be the major chunk of work in doing a V8M core. You then get into, so there's some sort of ancillary stuff like, okay, so what V8M core are we going to model? What board which has a V8M core in is the most useful thing to put that into? But yeah, the core CPU work would be the trust zone stuff.
Yeah, and I think for us, I'm from TI, working on getting secure runtime, secure RTOS going would be a use case where you're less concerned with the board level hardware as you are just the CPU model, and being able to use QEMU in the general sense with all the other tools we have would make it useful for those things. So like Zephyr in LITE or Embed or third-party type environments. So,
yeah. So the reason I mentioned the board model is just that QEMU's kind of its view of the world at the moment is definitely that we model CPUs, but the reason we model them is because we provide them in boards, and so you want to have some defined, this is the board we are modeling, just so that you've got some way of people being able to use the CPU support at all.
Okay, anything else? No? All right, well, thank you very much.